Here's problem 1918. A square plate has an area of 29 square centimeters at 20 degrees Celsius. It will be used in a low temperature experiment at temperature equal to 10 Kelvin, where it must have an area of 28 square centimeters. What area must be removed from the plate at 20 degrees Celsius for it to have the correct area at 10 Kelvin? The coefficient of linear expansion is 10 times 10 to the minus 6 per degree Celsius. Well, let's assume that we can have the correct area at the low temperature. So let's start there. So our initial temperature will be 10 Kelvin. And at that point, we're going to have an area of exactly 28 square centimeters. So we want to calculate what our final area would be when we heat it up. Our final temperature then will be 20 degrees Celsius. And adding 273.15 to that, we have 293.15 Kelvin. Okay. So, our final area will equal our initial area times 1 plus, and then for our area expansion, it's going to be gamma, which is 2 alpha delta T. So our initial area is 28 square centimeters. Alpha is 10 times 10 to the minus 6. And our change in temperature is going to be our final temperature, 293.15, minus our initial temperature, 10. All this in parentheses. So if we calculate that, 283.15 times 20 times 10 to the minus 6. Oops. Plus 1 times 28. I get 28.159 square centimeters. So that's what would happen if we had the perfect area at the low temperature and then we allowed it to expand to room temperature. It would be that size, 28.159 square centimeters. But we already are at room temperature and we have 29 square centimeters, so we can remove the difference between those two values. So we can remove 29 minus 28.159, which will give us 0.841 square centimeters. We're going to allow ourselves to remove that much from the original plate, giving it a size of 28.159 square centimeters at room temperature. Then when it cools down, it'll be exactly 28 square centimeters at 10 Kelvin. So that's how much we remove, 0.841 square centimeters.